Hello, everybody. So here's a problem where we need to minimize the cost of a box. Okay, and we're told that we need to construct an open-top rectangular box with a square base that must hold a volume of exactly 475 cubic centimeters. The material for the base of the box costs 6 cents per square centimeter, and the material for the sides of the box costs 5 cents per square centimeter. Okay, so we set up this problem by drawing a picture of the box. That's how I like to do it. Always draw a picture at the beginning. So let's see. Looks like this. It's a square base, so let's just put dimensions x on the base. And it has some height. Let's call that y. And what do we want to do here? What are we trying to do? Well, it says find the dimensions for a box that will minimize the cost of the materials used to construct the box. Okay, so let's write down a function that describes the cost of this box. Let's just put that over here. It's going to depend on the size of the box, so it'll depend on x and y. And let's see. The cost function will depend on the area of the base. So it's going to be, the area of the base is x squared, right? And the cost for the base is 6 cents per square centimeter. So it's going to be 6x squared. And then we have the sides are going to contribute to the cost. So the area of a side of the box is x times y, right? And there are 4 sides. And each side is going to cost 5 cents per square centimeter. So we multiply that by 5. So the cost function is 6x squared plus 20xy. That's our cost function that we want to minimize. So what we're going to do, well, we want to minimize this function. Right now it's a function of 2 variables. If we look at the problem, it says that, it gives us some more information. It must hold a volume of exactly 475 cubic centimeters. Okay, well that tells us that the volume of the box is 475. How do I compute the volume? It's length times width times height. So that means that x squared times y is 475. Okay, so I can solve this for y and then insert that into this other equation over here. Right? So let's do that. Y is equal to 475 divided by x squared. So what I'm going to do is I'm going to take this and plug it in for y over here. Okay? So what I ended up doing is I end up expressing the cost as a function of a single variable, just x, right? So really, I can view the cost function as a function of x alone. So we have 20x times 475 divided by x squared. Or if I simplify this, these x's cancel. 20 times 475, let's see, I did this ahead of time. I think it's 9,500. Wait, no. Maybe it is. Let me just double check. Yes, 9,500. 9,500 divided by x. That's the cost as a function of a single variable. Well, if we want to minimize the cost, we just use what we know from single variable calculus now to do that. We know that the cost is minimized when the derivative is equal to 0 or is undefined. In this case, well, let's just see what happens. We'll take the derivative of the cost function. That's this. Let's set it equal to 0. Oops, there's no square there. Sorry about that. Let's set it equal to 0. And see if we can solve this. Yeah, sure. I'll just add this quantity to both sides, multiply both sides by x. I get 12x squared equals 9,500. Okay, I don't know why I erased that. That should be there. for some reason I saw this and that and thought that I didn't made a mistake. This should be a square. Okay, so I add this to both sides, multiply both sides by x squared. This gives me 12x cubed, all right, equals 9,500. And so we solve this for x. So divide both sides by 12. And so x is going to equal, and then solve for x, we get the cubed root of 9,500 over 12. And you can simplify this down a little bit. You'll see that this contains a factor of 5 cubed, so a 5 comes out. So this is 5 times the cubed root. There's some other simplification you can do in here. I'll let you figure that out. It becomes 19 over 3. So we know that that dimension of the box has to be that many centimeters. All right, but we also have to find the height of the box. Okay, let's do that over here. So the height of the box, let's put it in this box. So the height of the box, well, we have an equation over here, right? We have a relationship between y and x, so there you go, just use that. So y equals 475 divided by x squared, but what is x? It's this, right? So if I square this, I'm going to get 25 when I square the 5, and I'm going to square this. So this is the cubed root. That's the same thing as raising to the 1/3 power. So if I square it, that's to the 2/3 power. And then you can do some simplification here. 25 goes into 475 19 times. You can do some more simplification and you will get down to, I'll let you resolve the details here. You can write this as 3 times the cubed root of 19 over 3. And that's the number of centimeters for the height of the box. So what we really did here is we've reduced this problem to a single variable calculus problem by using this equation here and then replacing one variable with the other one, and then you can write it as a single variable problem. And that is the answer.